In this very brief video, we will learn about DEPT NMR. DEPT NMR is a technique that is usually applied to carbon NMR and is used to be able to determine how many hydrogens are attached to the carbon that's responsible for a given signal. DEPT is an acronym that stands for Distortionless Enhancement by Polarization Transfer, and there's a lot of complex NMR theory behind all of this, but basically when performing an NMR experiment, what we're studying is the flipping of nuclear spins. Right? This process is not as simple as just going from down to up. There are all sorts of vector angles to take into account. There are these precession spinning factors that are taken into account. At the end of the day, one thing we can know is that in these experiments, what we're really doing is we're sending signals that will flip, for example, the carbon-13 nuclei by 90 degrees and then by 180 degrees. And along the same time, you can also flip the proton nuclei by 90 degrees or 180 degrees or whatever many degrees that you want to do. And by watching the amount of time it takes to go from, let's say, a 180 degree flip all the way back down to whatever the ground state is, or vice versa, that's how we get to the NMR data we actually see. So in DEPT NMR, this is what's called the pulse sequence. This is all just experimental detail. That's not really necessary at the introductory organic level, but the main thing to know for DEPT NMR is that there is a point in this experiment where we can change whether the last pulse here is at 45 degrees, 90 degrees, or at 135 degrees. And what you kind of see here is that after you do all of this, this is when you acquire the electric signal corresponding to all the resonances. And when that happens, what you get is an interesting phenomenon where in the case of a carbon with no hydrogens attached, the depth with 135 degrees pulse and the depth with a 90 degree pulse, both of those will just have no signal at all. If the carbon happens to have one hydrogen attached to it and three other things, then you'll get positive signals in both of these depth experiments. If it's a CH2, you'll get a negative depth 135 and nothing in the depth 90. And if it's a CH3 or a methyl group, then you'll get a positive depth 135 and nothing in the depth 90. And so this just happens to be a very convenient way for us to be able to determine, given a carbon, is it a carbon with no hydrogens, one hydrogen, two hydrogens, or three hydrogens attached. Let me give you a quick example of this. So this molecule right here is called diethyl phthalate, and it's often used as kind of a softener in plastics. If we're looking at this structure, this molecule is picked because it has all four different types of carbons when it comes to at least numbers of hydrogens on them. We can assign these various carbons like so. So those are all the different carbons in the molecule. So let me go ahead and assign these peaks for us. Turns out to be about like that. Turns out to be about like so. And what we can see is starting from the right side here with these methyl groups, those are CH3s. Those should have a positive depth 135, nothing in the depth 90. The CH2s, or the methylenes, is another term for that. Those are negative in the depth 135, nothing in the depth 90. The CHs on the aromatic ring here, those are in blue, so these are these two peaks. Those are positive, and they have signal in both of these two depth experiments. The last two carbons of the aromatic ring here are not attached to any hydrogens. Neither are the carbons of the carbonyls. So both those here shown in orange and red, this red one being the slight sliver right here, both of those have no signal except for in the non-depth spectrum. So DEPT NMR can be a very useful tool to help us pick between different types of carbons based on how many hydrogens we expect to be attached to those carbons.